Hello everyone, I'm Yiqian Wu from Peking University, China. It's my pleasure to present our work, Photolocalization via efficient probabilistic modeling of program semantics. Testing-based photolocalization has been a research focus in software engineering for a long time. The inputs of photolocalization include a faulty program and a set of tests with at least one failing test. The output is the suspicionist score of each program element. The program elements can be statements, methods, or other granularity. Among the large body of photolocalization research, a central focus is coverage-based photolocalization. The idea is that an element covered more by failing tests rather than passing tests is more likely to be faulty. For example, spectrum-based photolocalization, known as SBFL, counts the number of passing and failing tests covering the element. Then it calculates the suspicionist score of each program element by using these numbers. Here is an example of SBFL. These dots are the spectrum. However, how a buggy element causes the failure is more complex. Here is an analysis model named PIE. First, the test needs to cover a buggy element. Second, the buggy element results in errors in program state. Third, the errors are propagated to the output. Finally, the errors are captured by an assertion. From the analysis, we can find coverage-based methods only consider the first condition. But the latter three can also be very important, and they correspond to the semantics of the program. So, here comes the question, how to model the latter three conditions? To overcome this problem, different approaches have been proposed to take the latter three conditions also into consideration by analyzing the possibility of test failure when faults are covered. For mutation-based photolocalization, known as MBFL, it generates many mutations on each element. Then, it watches whether the test result changes. The idea is that if a change in a statement is more likely to change the test results in failing tests and less likely in passing tests, the statement is likely to be faulty. For angelic debugging, it uses symbolic analysis and modifies the result of an expression. If an expression can be modified to reverse the results of failing tests while maintaining the results of passing tests, the expression is considered more likely to be faulty. However, these approaches take the full program semantics into consideration. So, the analysis is inevitably heavy, which takes a long time. To this end, we propose a novel photolocalization approach, SmartFL. To analyze how a fault leads to the current test results, we model the probability of each statement introducing and passing an error by modeling semantics. Such analysis also requires efficiency, so we abstract the full program semantics. We introduce random variables to represent the correctness of each statement and runtime variable values. Also, we transform program semantics into probabilistic constraints between random variables. That is called efficient probabilistic modeling of program semantics. In fact, probabilistic modeling is a very promising direction in program analysis. We conclude two main advantages of probabilistic modeling. First, probabilistic modeling can parameterize the problem. It introduces parameters for elaborate modeling through proper division of different situations. Furthermore, it can optimize the parameters by learning. Second, probabilistic modeling can easily combine various information. It can encode various information in the form of probabilistic constraints and infer on a unified model. For example, semantic information, test results, heuristic knowledge, etc. Here, let's see a running example of our approach. We have a simple function foo with two tests. The condition a less than or equal to 2 at line 3 is buggy. It should be a less than 2. Both pass tests and fail tests follow the same child, line 3, line 4, and line 6. As a result, we can say coverage-based methods cannot handle such a situation because all statements are same in coverage. In this case, we need semantics. Now let's try to analyze it manually. We can find if line 4 or line 6 is wrong. The pass test is unlikely to pass because the return value is supposed to be wrong. However, if the condition at line 3 is wrong, the pass test can still pass because the correct condition may produce the same Boolean value as the wrong condition. Therefore, we can infer that the condition at line 3 is most likely to be wrong. Here we show how our approach models this program. On the left side of the table, we extract each statement. The corresponding probabilistic constraints are on the right side. For example, this D2 represents the variable value defined at line 2. This V2P is a Bernoulli random variable representing the correctness of D2 in the trace of past test. Now let's explain these formulas one by one. For line 2, it is the parameter, so we know D2 must be correct, and we have such formulas. For line 3, it takes the value of A defined at line 2 to calculate a condition expression. So we can know if both the statement S3 and D2 are correct, D3 must be correct. However, if one of them is incorrect, we set the probability to 0.5. That is because the operators like less than or equal to are insensitive. It means that these operators can sometimes still produce correct result even if their input values are incorrect. For example, for an expression like a less than 0, it gets true if a is minus, no matter whether a keeps the correct value. In summary, for insensitive operators like less than or equal to, we have 100% for correct to correct and 50% for incorrect to correct. Now back to line 4. The statement uses D2 to calculate D4. And there is one more thing. D3 should also be considered because the condition value controls where the program goes to line 4. If the condition value is incorrect, the calculated value D4 may also be incorrect. Another different thing is that for sensitive operators like plus, the probability of incorrect to correct should be very low. Now we set it to 0.01. For line 6, it is similar to line 4. The difference is that the effect of condition D3 disappears. Finally, from the assertion results, we can know D6 in pass test should be correct, and D6 in fail test should be wrong. After listing all these formulas, we can infer the probability of each statement being wrong. Here are the results. The statement S3 has the highest probability of being wrong, which is reasonable according to the oracle. Now let me describe the workflow of SmartFL. The first step is tracing. SmartFL instruments the faulty program, then selects some tests and runs them to get execution traces. The second step is modeling. SmartFL implements dynamic analysis to obtain data dependency and static analysis to get control dependency. Then it uses these dependencies to build a probabilistic graph. Finally, after probabilistic inference and dynamic slicing, it gets the final result. The probabilistic model we used is called factor graph. A factor graph is a bipartite graph representing a probabilistic distribution. The two parts of vertices are node vertices, the black circle, and factor vertices, the red square. In the graph, a node represents a random variable. A factor represents a probabilistic constraint and it links to the corresponding node with edges. A probabilistic constraint is actually a function mapping from corresponding variables to a real value. The factor value represents the likelihood of each situation. For example, here is the factor value table of this graph. We can see for f1, it is 0.4 if n1 is 1, and 0.6 if n1 is 0. This constraint says n1 is more likely to be 0 than 1. For f2 and f3, they also have corresponding probability constraints. Now let's see how the factor graph expresses the joint distribution. The column join is the production of all factors. It represents the likelihood of each line. And after normalization to make the probability sum to 1, we get the final joint distribution. And we can also get the marginal distribution of each variable. That is how a factor graph defines a probabilistic distribution. The problem is that the exact inference algorithm is exponential time. As a result, we use an efficient approximating algorithm called loopy belief propagation to infer the marginal distributions. Here we show how our approach builds the probabilistic graph. For nodes, we have statement nodes and value nodes. A statement node represents to the correctness of a statement, so one statement only corresponds to one statement node. But a variable corresponds to multiple variable nodes in the graph because a variable can hold a lot of runtime values during executions. For factors, we have evidence factors and semantic factors. Evidence factors are derived from what we already know. There are 3 rules. First, test inputs should be correct. Second, the Boolean value produced by passing assertion should be correct. And third, the Boolean value produced by feint assertion should be incorrect. And the function of our evidence factor is simple. If the corresponding node satisfies the evidence, the factor value is 1, otherwise it is 0. On the other hand, each semantics factor represents an assignment during execution. For example, let's see what happens to this statement in past test. On the graph, that factor is f2, connecting with n0, n1, n5, and n2. Here we extract the relevant parts. For that assignment, we can see n0 is the value it used, n1 is the condition value controlling it, and n5 represents the correctness of the statement itself. We call the conjunction of n0, n1, and n5 sources, and we call n2 result. Now let's see what is the factor value. The first 2 lines of the table indicate that if sources are correct, the result must be correct. For the last 2 lines, the factor value is different for insensitive operators like smaller than, equal to, and sensitive operators like plus, multiply. For insensitive operator, both 0 to 1 and 0 to 0 is set to 0.5. And for sensitive operators, the former is 0.01 and the later is 0.99. However, there still exist 2 main challenges. The first one is about control statements, including how to find the influence boundary of a condition expression and how to model unexecuted statements. Our solution is to combine static analysis and dynamic traces into a unified model. The second challenge is about scalability. There can be many long test execution traces. They result in a large probabilistic model, which is hard to inference. To overcome scalability issues, we try to select and compress the traces. Also, we apply an efficient probabilistic inference algorithm. Now it's about the first challenge, how to model unexecuted statements. For this program, the buggy line is line 3, and let's see how the fail test runs. It goes through line 3, line 7, line 9, and line 11. But there is no assignment for variable a at all, so our model cannot relate this fault to the condition expression at line 3. To handle this problem, we can transform the program into an equivalent form like this. We add some dummy statements like a equal to a. Now the condition at line 3 controls that dummy statement. As a result, it will relate to the final result. To add such dummy statements, we implement a lightweight static analysis only considering variables on stack. Here is the second challenge, scaling. On the one hand, we need to reduce the size of traces. The first thing is about compressing loops, for the reason that heavy loops can make traces very long and undermine the efficiency. Back to our model, exactly identical sequence can provide additional information, so we can remove them from the model. The rule is that if the sequence of statements executed in 2 iterations are identical, we only keep the first iteration. We first compress the inner loops and then the outer loops. For example, a long sequence like this is transformed into that short sequence. Second, we only instrument methods covered by fading tests because they are critical. For a passing test, an uncovered method is treated as an atomic statement while modeling. On the other hand, we select test cases. In reality, a project contains a lot of tests. Most of passing tests don't relate to the fault, so we decide to discard some passing tests for scaling. We first run a coarse-grained instrumentation to get method-level coverage. Then, we rank passing tests by the number of commonly covered methods with fading tests. Finally, except for the top 50 passing tests, the remaining tests are excluded. Also, we limit the total length of added traces. First, we add all fading test traces because they are critical, and then we sort remaining passing test traces in ascending orders and add them one by one to the graph till the limit. Here is experiment setup. We choose 4 projects from defect4j as benchmark, 222 faults in total. According to existing research, we select OGI and D star from SBFL, Metallics and Muse from MBFL for comparison. We don't compare with angelic debugging because there is no implementation scalable to large programs as far as we know. We choose top K where K is 1, 3, 5, and 10 as measurements. Our method focuses on statement level. For method level evaluation, we calculate the suspicious score of a method as the maximum suspicious score of its statements. And here are the results. At statement level, we can see SmartFL performs better than other methods, especially on top 1. For statistical significance, we implement a sign test on each pair of techniques, considering the faults where at least one technique has a top 10 result on it. The results show SmartFL significantly outperforms OGI, D star, and Muse, while still having more positive compared with Metallics. For method level, SmartFL performs better than Metallics and Muse, and still has an advantage over OGI and D star at top 1. For efficiency, we count the average running time for each method. The average time of SmartFL is about 210 seconds, much smaller than MBFL method. CombinedFL is a technique for combining different photolocalization methods. It is a state-of-art photolocalization technique on statement level. We combine SmartFL with CombinedFL Level 2 and Level 4. Level 2 contains only lightweight methods that require minutes to run, and Level 4 further includes predicate switching and MBFL, requiring hours to run. We can see the top 1 number raises from 45 to 58 by replacing MBFL methods with SmartFL, without any decrease. On the other hand, combining SmartFL with Level 4 results in better top 5 and top 10 accuracy. In summary, here are the main contributions of this paper. First, we propose a fault localization approach by efficient modeling of program semantics. Second, We propose novel techniques for modeling the control statements and for addressing scalability. Third, we perform an evaluation on the defect4j dataset to show the effectiveness and efficiency of our approach. Our tool and evaluation data are publicly available on GitHub. Welcome to follow our work and get in touch with us. Thanks for your listening. See you at ICSE 22.